So waves can interact with each other, and when the waves are in phase, they make bigger waves. This is called constructive interference. So this is illustrated down here. If the waves are in phase, meaning their peaks are lined up and their troughs are lined up, then they constructively interfere and they make a wave that has larger amplitude. Their amplitudes add. We can also have destructive interference where the waves are out of phase. So here the peak of one wave lines up with the trough of another, and then they'll cancel each other out, and that's called destructive interference. This is sort of the thing that happens if you've ever bounced on a trampoline with someone else. And if you bounce just right, you can bounce extra high, and other times you're like, that didn't go anywhere, right? Because it depends on whether you're in phase with the other person or out of phase, right? Another thing that waves do is called diffraction. When traveling waves encounter an obstacle or an opening in a barrier, if that opening is about the same size as the wavelength, the waves will bend around it. Traveling particles do not do this. So the diffraction of light between two slits is comparable, let's start that one over. The diffraction of light through two slits separated by a distance comparable to the wavelength interference results in an yeah, you can read that. We'll see this illustrated. Interference patterns are characteristics of light waves. So the light goes through two slits and it makes this diffraction pattern. This is what I was trying to say in words. So here, what we're seeing here, this series of lines, we're looking like down on top of the wave. The waves are oscillating up and down, and we're looking at the tops of them, and so this is showing where's the crest of the wave. So the wave is going in and out of the screen here. As the wave comes to this barrier, there's a hole here, and this slit is about the same size as the wavelength. And when the waves hit this, they'll go through the barrier, through the slit, and then they will be curved. That's called diffraction. Particles don't do that. If you have particles coming at a barrier, they either hit the barrier and bounce back, or they hit the hole and they go through. So particles and waves behave differently when they encounter a slit in a barrier. Any questions yet? Well, we understand what the particles do, right? Yeah. The waves is a little less clear. If you have two slits, then you can see the interference. So here we have one light source, and it's sending out waves. And as the waves hit the slit, they diffract, and they form a new curvature. And so then it comes over here and hits this slit. And so now we have these two waves that are traveling out, and they have the same wavelength, and they're going to interact with each other in different ways. Sometimes they're going to overlap and constructively interfere, and sometimes they will destructively interfere. Depends on the difference in the path length. And so we'll see this sort of a pattern of stripes, light and dark. So I'm going to show you a video which does a much better job of this than we're talking about it. And then we can look at the diagram again. Come on. There we go. It only took forever.
If it were like the stock, if everybody be doing it, they're not rich, and you know there's a reason why.
Ads.
What is light?
What is light? What is light? That's a good question. What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras.
We all have auras.
Which are light?
Yes, they are. It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The color.
It goes in your eyes and then you see stuff. They range from white to red to orange to grey. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right,
Yeah.
it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances, besides the fringes of colors on each side of the shadow. The shadow itself was divided by similar parallel fringes of smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
And you could take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. What I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
Well, the obvious thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box. Two bright bands.
Two little lines. Yeah. I think it'll be one line instead of two.
I can expect to see the whole box lit up.
That'll probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Well, there's one in the middle strongest, two either side.
The two on the outside are multicolored. The one in the middle is just white.
Part of a rainbow?
The rainbow of colour as well.
Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits. That's incredible.
But all we're doing is we're putting a light through two very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved there. The average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light canceling itself out.
This is basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Exactly the same
And
pattern.
they go and overlap. As this ripple overlaps with those ripples, down the bottom, you get a series of, you get like a bright spot, and then a dark spot, then a bright spot, then a dark spot, then a bright spot.
Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. So you saw the ones to the right were slightly colored.
Yeah,
that's because
working.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences in different wavelengths.
Exactly.
That's amazing.
So the difference
So
between
there's
red
still
and blue,
that red bin over there, the green part, I'm seeing
It's a
that,
different-
it's just different
different
wavelength. And that's how we bring in all these beautiful colours all around us.
exactly.
That's amazing. I'm amazed. Oh, good on you, thanks, Ben.
Hey, thank you.
I have been enlightened, literally.
Okay, so questions? I really like that video because they did a great job of making the ripples on the pond. And so the ripples on the pond, he was bouncing 2 balls up and down and making ripples that came out like this. And then you could see as the ripples overlapped with each other, there were places where the waves got bigger and places where the water was flat. They canceled each other out. And so that's how we get this pattern of the bright spots and the dark spots. So that's something that waves do. Okay? Particles don't do that, but waves do that. Anybody have any questions? So from that experiment, it's clear that light behaves as a wave. Light also behaves as a particle. And this is demonstrated in the photoelectric effect. So many metals will emit electrons when a light shines on their surface. Classic wave theory says this is the light energy being transferred to an electron. And this theory says that only the intensity, the amplitude of the light, would affect the emission of the electrons. So this predicts that if you used a dim light, that it would take a while, there'd be a lag time, before electrons were emitted because they would have to absorb enough energy before they could be ejected. So this is the diagram. This is the setup here. So we've got a metal surface here, and the light comes in, and the light can eject an electron from the metal surface. Now we can't see the electrons, so how do we detect them? Well, we're doing this inside of an evacuated chamber, and we've got an electric voltage across here, so this is negatively charged and this is positively charged. And when this electron gets loose, it's going to be repelled by this negative surface and attracted to the positive terminal. And when it gets across this empty space to this electrode, then we can detect the flow of current and we can measure that. So experimental observations gave the following results. So here what we have is the rate of electron ejection as a function of the frequency of light. And so at low frequencies, there was no ejection of electrons. And it didn't matter how long you waited, the electrons would never get ejected. So when we got to this frequency, this is called the threshold frequency. When you got to a certain frequency, then all of a sudden electrons would start being ejected. Well, the photoelectric effect is that the light, the photo part, can kick out electrons. So the photoelectric effect demonstrates the particulate nature of light. So we get to a certain frequency and we'll get electrons being ejected. If we go with a higher intensity light, we get more electrons. Lower intensity light, we get more electrons. But when we increase the frequency beyond that threshold frequency, there's no change. It doesn't matter how high the frequency is. We still get the same rate of electrons being ejected. And there's no lag time involved in this at all. So that wave theory wasn't working out, doesn't match up with these results. So Einstein explained this by proposing that light energy was delivered to the atoms in packets. A packet of light is called a quantum or a photon. So a photon is a piece of light. Like I'll have a piece of milk. I'll have 2 pieces of milk. What? You can't have pieces of milk. It's a liquid, right? How can you have a piece or a packet, a quantity, an individual piece of light? It's just hard to get your mind around. So the energy of the photon of light is directly proportional to its frequency, nu. And I got the Greek thing in here, and I meant to put these in previously, but I screwed up. So there's the Greek nu frequency. And it's inversely proportional to the wavelength, lambda. So there's a proportionality constant, h, it's called Planck's constant, and it has this values, come on, the pointer, 6.626 times 10 to the minus 34 joules seconds. You don't need to memorize that, I'll give it to you. But the energy of this photon is equal to this constant times the frequency. Or we could also say the energy is equal to the constant times the speed of light divided by the wavelength. Because c over lambda is the same as nu. And we're going to get back to the photoelectric effect. A 100-watt light bulb radiates energy at a rate of 100 joules per second. The watt is a unit of power, which is energy over time, and that's defined as 1 joule per second. If all the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? Assume 3 sig figs. Okay, this comes down to being a dimensional analysis problem. We can do this just by figuring out the units. So what do we have here? We have 100 joules per second, and then we have a wavelength of 525 nanometers. It wants to know how many photons per second. So that would be how many photons in 1 second, right? Photons per second. Number of photons in 1 second. So I'm starting with 1 second. So I'm going to stick it up at the top. So I'm starting with 1 second, and I want to end up with the number of photons. I have this relationship that's joules to seconds, so I could figure out how many joules are happening in 1 second. It's 100, right? And this wavelength here would allow me to calculate the energy of the photon. So the energy of the photon is equal to hc over lambda, where this is lambda. So we need Planck's constant, 6.626 times 10 to the minus 34. Correct me if I get that wrong. Joules times seconds. And the speed of light, 3.00 times 10 to the 8th meters per second. And divide by the wavelength, because the speed has meters in it, I want the wavelength to be in meters as well. So 525 nanometers is the same as 525 times 10 to the minus 9 meters. And so then when I look at what happens with the units, the seconds cancel and the meters cancel, and I'm left with joules. That's a good question. Where did I get the 6.626? It's right here. Well, the pointer won't move it. It's a constant. So 6.626 EE minus 34 times 3 EE8 divided by 525 EE minus 9 is 3.7862 times 10 to the minus 19 joules. That's the speed of light.
The speed of light.
It's 3.00 times 10 to the 8th meters per second. It's another constant. So H is 6.626 times 10 to the minus 34 joule seconds. And C is the speed of light, 3.00 times 10 to the 8th meters per second. And those are not things you need to memorize. In fact, you don't even need to memorize this equation, but you need to be able to find it on the page and use it. So this is the energy of that light. It's the energy of one photon. So that many joules equals one photon, one piece of that light. So that allows me to convert from joules to photons. Kind of made it a lot longer than it needed to be there. So 1 second times, I'm going to joules, dividing by seconds, and then going to photon, dividing by joules. This is the power, the joules per second, 100 joules per 1 second, given in the equation. From the wavelength, I was able to calculate the energy of a photon of this light, 3.7862 times 10 to the minus 19 joules. So 1 times 100 divided by 3.7862 times to the minus 19. It says use 3 sig figs. 2.64 times 10 to the 20th photons. Now, if you've ever watched Star Trek, you know you've heard photons, right? Fire the photon torpedoes! But, you know, we just kind of hear it and we're like, oh yeah, that's a kind of torpedo, great. But what is a photon? A photon is a piece of light. So could you blow something up by shooting light at it? Actually, you could, because there's energy in it, right? So that many photons. Come on. Having technical difficulties. Here's sort of another related kind of problem. Arrange these three colors of visible light, green, red, and blue, in order of increasing wavelength, increasing frequency, increasing energy per photon. This sort of question is really common on the ACS exam. They want you to put things in order, right? And so people find this confusing. So in order of increasing means I put the small one first, and then the medium one, and then the biggest one. Okay? So I've got three things here about this light that I need to order: wavelength, frequency, and energy. So if this was a test question, and it could be, and I don't have the electromagnetic spectrum diagram to look at, how could I figure this out? So this is how I would think through it. First of all, I'd think Roy G. Biv. So here's the light, Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. And then I ask myself, well, what's next to violet? Ultraviolet, right? So here's UV. And what comes before red? Infrared. And that helps me to remember which end of this has more energy. UV light is what gives me a bad sunburn. And looking at me, you can probably figure out why that is, right? I just burn like nobody's business. So this is high energy. That means this side must be low energy. So the colors that I'm looking for in this problem are red, green, and blue. So energy per photon is the last one, but we could do that one first. Which one of these colors has the lowest energy? Red. So it's going to be red, and then what's bigger? Green, and finally, blue. Everybody okay with that? So then it also wants wavelength and frequency. So then I'm going to think, well, I'm going to draw a couple little pictures for myself here. I'm going to draw this wave, and then I'm going to draw this wave. Which one of those looks like it has more energy? The one on the bottom just looks more energetic, right? You know, imagine it's jumping up and down. It looks like it has more energy, and it does have more energy. Because if you were standing here at the ocean and these waves are hitting you, this one's just going to be beating you rapid fire. You're just going to be knocked over. And this one, you've got a little time in between to recover.
So would it be similar to surface area?
No, it isn't. It isn't related to surface area. So then I look at this one and I say, well, this is high energy. And this one up here is low energy. Which one of those has the longer wavelength? The one on top. This is this low wavelength. Right? It's shorter. And this is the high wavelength, or long wavelength, right? I'm sorry. Short wavelength. High, low, short, and long. This is so confusing. Short wavelength. Okay, so now we could look at A and compare wavelength. Well, which of those has the shortest wavelength? The shortest wavelength, is the one with the most energy. Right? So high energy, short wavelength. High energy, so that's going to be blue. Blue's going to have the shortest wavelength. And then what's in the middle? Green And what's got the longest wavelength? Yeah, see, here, let me fix this. I screwed it up. It's supposed to be long, not low. Sorry about that. And then the longest wavelength is the red. I get everything straight now. Long, short, high, low. So frequency is opposite of wavelength. It's inverse. And so you could just say, well, the frequency is inverse of the wavelength, it's going to be the opposite order. Or you can think about the pictures and say, well, if I'm standing here and here, these two people, who's getting hit more frequently? These waves are going at the same speed. The guy at the bottom's getting hit more frequently, right? This is higher frequency, high energy, high frequency. So then frequency, the high energy is the high frequency, so the blue is at the high end, and the red is at the low end. And green's going to be in the middle every single time. Okay? So that's how you think that one through. So back to our photoelectric effect. So when we have one photon that has that threshold frequency, remember frequency is related to energy, it has just enough energy to dislodge one electron.
So back to the other side.
Mm-hmm.
So will the energy per photon and frequency, they should always be proportional, right?
Yes. Energy is proportional to frequency, and energy is proportional to 1 over wavelength, because frequency is proportional to 1 over wavelength. Yeah. So there's a minimum amount of energy required to kick an electron out of this metal surface. It's called the binding energy. And it's given the symbol phi. It's a Greek letter phi. It's kind of like a small circle with a vertical line through it. That's the binding energy of the electron. So if you put in the binding energy, that's just enough to break loose the electron. If you put in higher frequency, if you put in more energy, you can also break loose the electron. But one photon still is going to break out one electron. Then where does the extra energy go? The extra energy goes into kinetic energy of the electron. It goes off moving faster. So the kinetic energy of the electron is the energy of the photon minus the binding energy. The energy of the photon is h nu, Planck's constant times the frequency. Subtract the binding energy. Okay, so that's all a little bit hard to understand. This is like little boys going to Disneyland. Okay? So the binding energy is the price of admission. If you go to Disneyland, and let's just say it's $100, it keeps changing. Maybe it's $1,000 by now, I don't know. Let's just say it's $100 for a one-day ticket to Disneyland. So you go to the gate and you have $95. Are they going to let you in? No, because it's $100, right? They have no compassion. It's you have enough money or you don't. So if you have $95, they won't let you in. What if you have $105? Sure, they'll let you in. They'll take your $100, you get to keep the $5, and you get to go in. And what are you going to do with the $5? Spend it on stuff, except there's probably nothing you can buy for $5, right? So let's say you show up with $200. They'll take $100 at the gate, and you go in, and you have $100 to blow at Disneyland. And you get some chicken McNuggets and a soda, and maybe a pencil, right? I don't know. They have chicken nuggets, though. Yeah. I don't think they have McDonald's. I haven't been there for a long time. It's too expensive. 6 children? like a whole summer vacation kind of thing. Anyway, so to get into Disneyland, you have to pay the admission, and then if you have more money than that, you've just got more to spend, right? So with the electrons, there has to be this minimum amount of energy to kick the electron out, to get it through the gate. And if it's got more energy, it just takes that energy with it as kinetic energy. It just goes off moving faster. So there's no energy lost. It's just going faster. Does that make any sense? But if you come to Disneyland and you don't have enough energy, you don't get in. You can't just stand there and wait. It's you have enough or you don't. And so there's no lag time on this photoelectric effect. The packet of energy comes in, this photon of light, it either has enough energy to dislodge an electron or it doesn't. If it has enough, it will dislodge the electron. If it doesn't, it just bounces off. So the threshold frequency is the binding energy. Yep. That's the minimum frequency, the minimum energy to kick out an electron. Exactly. So here's sort of a thinking experiment. So suppose a metal will eject electrons from its surface when struck by yellow light. What's going to happen if it gets struck with ultraviolet light? Well, we have to decide, is ultraviolet light higher in energy than yellow or lower? It's higher, right? So ultraviolet's higher in energy, so is that going to be able to dislodge electrons? Sure. So now we can look at these choices. A, no electrons would be ejected. Well, that's not true. The electrons would be ejected and they would have the same kinetic energy as those ejected by the yellow light. So yellow light will eject electrons, and the ultraviolet will eject electrons, but the ultraviolet has more energy. So this is the kids at Disneyland. They have more money. So the kinetic energy is like the money they have to spend on stuff. So this isn't true because they're going to have a different amount of kinetic energy. The electrons would be ejected and they would have greater kinetic energy. Yeah, that's the correct one. So we're striking with ultraviolet light instead of yellow. The light has more energy. The electron gets ejected. That's a certain cost in energy, the binding energy. And the difference, the excess, goes towards kinetic energy. So the ultraviolet light gives more kinetic energy to the electrons. So the last choice, the electrons would be ejected, but they'd have lower kinetic energy. That's not correct. Any questions?
Okay, can we go back to your Disneyland?
Yes. Mm-hmm.
All right, so the binding is the price of the
Yes.
And then the photon is the energy that's coming in.
Yeah, so the energy of the photon is how much money does the kid have when he sets out to Disneyland? The binding energy is what he has to pay to get in, and the difference between what he came with and what he had to pay to get in is the kinetic energy, how much he has to spend at Disneyland. You like that? Yeah. I love analogies. Yeah. Some of them make more sense to me than to my students. Yeah. Any other questions? So why does this demonstrate that light behaves as a particle? Because we have this piece of light has a certain amount of energy. If it was a wave and you just had energy coming in, then you should just be able to wait until there's enough energy and then the electron would get ejected. But you either have enough energy or you don't. This piece of light either has enough energy to eject an electron or it doesn't. If it doesn't have enough energy, nothing gets ejected. You can't just wait until they build up. Does that make sense? So diffraction shows us that, and the double slit experiment shows us that light is a wave, and the photoelectric effect shows us that it's a particle too. So this is called the wave-particle duality. Sometimes light seems to behave like a wave, other times it behaves like a particle, and which behavior you observe depends on the particular experiment. You can't see both behaviors at the same time. So this is the cat is dead or the cat is alive, right? When you observe it, it's one or the other. If you're not observing it, it's both at the same time.